Hello and how are you? Welcome to this tutorial in which we are going to handle the final part of the theory with respect to differentiation. So still under calculus or elementary calculus, and I am your tutor Doug Joseph Adeli. Let's humble ourselves for word of prayer. Father Lord in heaven, we ask that you are able to teach us this last bit before we embark on our practice. We pray that Lord you are able to be with us. Just may pray. Amen. Now, focusing on our specific objectives to be able to see of what we have achieved so that we can be able to wrap up differentiation. By the end of this topic, basically by the end of this tutorial, you should be able to find average rates of change and instantaneous rate of change that was covered earlier enough in the covering of the course. Finding the gradient of a curve at a point is also another thing that has been covered. Relating delta notation to rates of change also has been covered. Finding the gradient function of a function of the form y is equals to x power n, and also defining derivative of a function, derived function of polynomial, and differentiation. Determining the derivative of a polynomial, finding equations of tangents and normals to the curves, and also sketching the curves. All these have been able to be handled. So in this tutorial, we want to apply differentiation in calculating distance, velocity, and acceleration, and applying differentiation in finding maximum and minimum of a function. Now, basically, we are going to summarize this into one topic called application of differentiation. And basically, we are looking at it in a broader sense, not only in classwork, but also in the extra fields of work. So probably I may just come about and ask, do you know what differentiation is? Because most people, you find that they tend to be able to miss out of what differentiation is, and their main definition of differentiation is usually the act of just deriving and deriving things. It's not bad, but you are missing out the main step. So if I check from my dictionary, you find that under calculus, differentiation is the process of determining the derived function of a function. Okay. You may say so, but it is quite good important to be able to add more to it, to be able to find out how can I apply it. Differentiation in life, all that you have done, how can it be applied in normal life situation? So if I just go to my dictionary so that I may apply from various understanding points that you know to be able to bring home of what differentiation is, you find that differentiation, if you just look at the word different. So differentiation is the act of having different things, just as by the way. So differentiation is the act of distinguishing or describing a thing by giving its different or specific difference, and in other words, you mean by giving the exact definition or determination. For example, you may have a broader picture of a lion, but in that lion, the lion might be having spots, and that spots may be because of arrows that people are shooting it at, but it sustained just injuries and maneuvered away. Someone else may decide and say, if you look at this lion, it is missing an eye. Or if you look at the lion, the whiskers are very long. If you look at the lion, the paw, for example, it doesn't have the nails. So that is the act of differentiation, giving finer and finer details. Something that is more tangible to be able to explain this, you find that in geology, differentiation is the act or the process of separation of cooling magma into various rock types. So you find that, for example, if you have different rock types, you may find you have gypsum, you have glass rock, you have pumice. They all come from magma. Why? Are they of different characteristics and different formation, different features? It's because of the cooling what? Cooling rate. So the rate at which they cool, that is very important, the term rate. So to be able to wrap up our understanding of what differentiation is, I would like us to note the following. So we are basically looking at finer details. So narrowing down from a very big thing to a very small thing to be able to give us more vivid explanation. For example, I may have an understanding that someone drove a car from Mombasa to Nairobi, but in a very uh, clear manner, or a more distinguished guy who is very clear in analyzing things, he'll decide to say, at a particular time, this car was at a particular place. At a particular point, he was at this particular place. That's what differentiation is all about, giving those finer details. So basically, differentiation represents the rate of change of a function. That is clearly what differentiation is. If you understand that, we are good to go for the application differentiation. So basically, if you have a big term and you want various finer details to explain that big term, you basically apply differentiation. So differentiation is applied in diverse fields in real life situation. At this level, you shall work heavily with kinematics plus other functions with respect to the examiner. Now I've mixed, just summarized a lot of things there. You find that right now, because you're preparing for your normal exams, and also it's because the teacher came and taught you about differentiation, you expect that he'll be giving you functions and then you differentiate them. You should have a broader picture of what differentiation is. You are going to be able to heavily tackle kinematics, and you may find instead of kinematics only, someone comes about with another formula different from kinematics but requires you to differentiate. That's what I mean, plus other functions with respect to the examiner. So, but the main questions to ponder on is what does differentiation entail, and that's what I've been clearly trying to explain so that you may get what differentiation entails. It entails the rate of change of a function, or basically narrowing down to finer details from a magnified point of view. Not a magnified, from a larger point of view to a magnified point of view. That's what it should be. So differentiation entails the getting of finer details from a greater data in terms of rate of one item with respect to another. So for example, we have been used to saying we have dy over dx. So we are differentiating a function which is, for example, y is equals to x squared. So from x squared, we can now come down to either first derivative or second derivative, third derivative, which become even smaller and smaller items. And that, for example, the y is differentiated with respect to what? To x. No wonder you have dy over dx. With the time, we shall be able to notice that we have ds over dt, and those ds over dt have meanings. For example, s being displacement and t being time, you find that it will mean something else. Kinematics deals with displacement, which is denoted by small letter s, velocity or speed by small letter v, and acceleration by small letter a. That's what kinematics deals with. So from linear motion, we know the relationship of these parameters, or basically I simply mean their formulas. Now we know that displacement is the product of velocity and time. Velocity itself is the quotient of displacement with respect to time. Time itself is also a quotient of displacement with respect to velocity, And finally, acceleration is the quotient still of the difference of velocity with respect to time, or you can say the rate of change of velocity with respect to time. Now, from linear motion, what I've just simply done is just to explain mathematically what these terms are. But from physics point of view, or even linear motion that you learned earlier in mathematics, you know that displacement is basically uh, the distance covered by a body in a specific direction. Velocity in itself was said that it is the rate of change of displacement per unit time, or with respect to time. Time itself is also the rate of change of displacement with respect to velocity, or the rate of change of displacement per unit velocity. Whereas we find out that acceleration is the rate of change of velocity per unit time. So mark those particular definitions if you had forgotten, or if you remember them, please let them ring in your mind as we get deeper into applications of differentiation. Now, let's prove something here. Let's prove our say. We have said something about rate and rate and rate and rate and rate. Differentiation has also some rates and rates and rates. Let's prove if there is a relationship between them. So let me just take you back. Notice the aspect of time is common in each and every of these parameters, and heavily it is in let me start from far behind a bit. Find that time is an independent variable. I believe that we agree with that, because it does not depend on any other thing to be able to define itself. Reason being, with whether you cover a particular distance or whether you go at a particular velocity, time shall still be the same and shall go in a particular dimension. So time is an independent variable when you are dealing with kinematics. So it being an independent variable, it means if we check each of these parameters, displacement, velocity, and acceleration, they can be defined with respect to time, as you can see from their various formulas. Because of that, I suppose that there's a way they should be related in terms of differentiation. So that's what I want us to prove here. That's what I mean by let's prove our say. Let's begin from displacement to velocity. Is there a relationship between the two? We know that displacement is the product of velocity and time. Now, if I differentiate distance with respect to time, I'll figure out that velocity, it shall be my constant. Reason being, I'm differentiating displacement with respect to time. So my velocity shall be a constant. Therefore, if I differentiate this, I'll end up having ds over dt is equals to v. And v is velocity. And ds over dt is basically the rate of change of displacement with respect to time, ds over dt, which is also part of what differentiation is all about. So this one clearly tells us that there's a relationship between displacement velocity, which means if I differentiate the function of displacement, I'll get velocity. And if you check even from dimension analysis, the formula for velocity, which is displacement divided by time, is meters per second. Whereas the rate of change of displacement per unit time is still meters per second. Therefore, I'll be able to be confident and say that if I differentiate function of displacement, I'll get velocity. So that is one thing that you need to know. So if I have a big broader term of displacement, a car moving from Nairobi to Mombasa, I can be able to narrow down and say I would like to get the average velocity, or I'd like to get the instantaneous velocity at a specific time. Simple like that. That is differentiation. What of velocity to acceleration, since we have said displacement to velocity is there? Let us see if this other one exists. We know that velocity is equals to displacement divided by time. Now, could you please now try fumbling around that? Because now this one seems quite a new thing. It will be good if you try to fumble about this one. Since you have seen how I've explained the first part, you can try working out the second part. Supposing that you have something, the first step we said, if you have mixed fraction like that, you basically begin by simplifying everything, whereby v will be equal to the product of displacement and t, whereby it's an inverse, raised to power -1. So if I differentiate velocity with respect to time, I'll end up with this. I believe everything is correct, whereby if I finalize everything, you'll find that dv over dt is equals to s over t squared. Now, something of interest. S is in meters. Let me just write it there. S is in meters, whereas t squared is second squared. What is the units of this? This is acceleration. Hold on. We know that s over t squared is meters per second squared, which is acceleration, correct? And we know that acceleration is the rate of change of velocity per with respect to time. Therefore, acceleration is basically, if we differentiate the function of velocity, you basically get acceleration. Now, let me just narrow it down and be able to make a chain link. If I differentiate the function of displacement, I'll get velocity. That same velocity function, which is ds over dt, if you differentiate it further again, you shall get acceleration, simply because you are simply working with the same thing. I believe that now makes sense. That means if you had your function as displacement, if you differentiate it twice, your second derivative shall be equated to acceleration. The first derivative shall be velocity. I believe that now makes quite clear sense. Now, differentiation is not all about kinematics only. You may have it in other fields, for example, volume, area, and all the other things. I hope you're not very surprised about that, because that is also differentiation, because we are narrowing down from a very large portion of material, and you just want an aspect of length, for example, or area of that particular cuboid or box or whatever it is. So differentiation can also be applied in volume to area, from volume to area, whereby you can have the volume of a cube, which is L cubed. So differentiating volume, by the way, let me begin from this far away so that you may not be confused when I start explaining things. If you differentiate volume with respect to any dimension, here we must note that it's dimension. So the differentiation of volume with respect to dimension will give you area. Now let's prove this. For example, if my area is m cubed divided by a dimension of meters, this gives you what? Square. Now let's prove it by differentiation. If I have the volume of a cube, which whereby you know it's L cubed, so the derivative of it will be dv over dl, which will be equal to 3l squared. L squared, what is the unit of L squared? Meters squared. What about a cuboid? You'll have length times width times height. Yes, correct. So depending with the dimension that you shall be differentiating with respect to, I've decided to say dw, so that you don't say, you see, he just used dl. No, it's just in dimension. So it will be dv over dw. If I differentiate that, L and h will be held constant. So if I differentiate that, you'll find that this is still area. What about that of a cylinder? The same thing. If I differentiate with respect to r, which is the radius, you'll end up with area. I believe you can notice that here. So you'll end up with the surface area of a curved part of that particular cylinder. So see how things are quite easy. If you have been given the volume of a cylinder, should you start wondering about the what, I don't know, all those things? We just differentiate here. Most examiners will find that because you have learned about differentiation, they'll end up giving you questions. For example, you have been told the volume of a cylinder is, for example, 20 cubic meters. Find the curved surface area. For example, find this, find that. So that's what they can be giving you. So be prepared for either of those. So that is basic differentiation. If you learn about that and be able to appreciate differentiation in that particular dimension, well and good. By the way, please wait for a tutorial that is coming ahead on combining both integration and differentiation. It shall just be a super thing that I'm yearning to be able to share it with you. Otherwise, let's continue with application of differentiation. Important terminologies you should never forget. 1. Maximum displacement occurs when, for example. Now, I'm not speaking majorly about maximum displacement because it's not only displacement you shall be working with. There's a question that is on the slides that shall be handling about volume, and the term maximum is also there. So maximum, when somebody is telling about maximum, now here I've only chosen maximum displacement. Now, if I'm dealing with maximum displacement, I need to figure out myself in the shoe of displacement. So when does maximum displacement occur? Maximum displacement occurs whereby the velocity is highest. I believe it makes sense. When I go very slowly, but somebody goes very fast at the highest velocity can be able to reach, he'll cover a very large distance in a very short span of time. So the maximum displacement is covered when the velocity is highest. I believe that one we agree. Now, if my velocity is highest and I've been given a displacement function, by the way, how will you even get the maximum velocity? Most cases you usually don't get the maximum velocity. I'll give you a question here and it shall be quite interesting. The relationship that comes about is proportion. When you have maximum velocity, the acceleration is usually 0 because I've reached my maximum velocity. I'm not increasing the velocity again, so there's no acceleration continuing. So that's why we say when there is maximum displacement, it occurs when acceleration, which is dv over dt, is equals to 0. And that is only and only when velocity is maximum. Next point. What if somebody tells you a particle is momentarily at rest? What does it mean? Or a particular car was momentarily at rest after traveling at a particular time. It simply means the velocity is at rest. It's at 0. The car is at 0. The particle is at 0. So that's what he basically means. Those are various terminologies you should never leave behind. Now, what about this one? If somebody tells you find something during a particular period, for example, the most common one is find the distance or find the velocity or find the acceleration during, for example, the 5th second. What might he mean? Does he mean that you find the displacement after 5 seconds? No. It simply means during the 5th second, at that time. When that time here, for the 5th second, sorry for the mixing languages, when the clock ticked, for example, between 5 and 6, that is what we mean by during that particular time. So during the 5th second, it simply means between the 4th second and the 5th second. So the range you are working with to get the displacement covered is between 4th second and the 5th second. I believe those are the main terminologies that we usually have that majorly confuse students. Please don't forget that. Now, if I just go back to this statement here, in a question you'll find someone asking you find the maximum displacement, or someone will tell you find the maximum velocity. The approach will be the same because they all tie to acceleration being 0. Let's now start working on examples. First, the displacement in meters of a particle is given by s is equals to t cubed over 3 minus 3t squared plus 5t plus 10, where t is time in seconds. Find 1. Velocity and acceleration after 2 seconds. 2. Time when the particle is momentarily at rest. 3. Time when the acceleration is 20 meters per square second. 4. Maximum displacement attained by the particle. And then 5. The displacement covered by the particle during the 5th second. Now notice various good questions here. So if you don't mind, you may pause the video from what I've just tried to label and explain. Try putting them into practice in this question before I give you what I basically have. I suppose that you have something on the table. In the first question, you have been told given that is the displacement function in meters, find the velocity and acceleration after 2 seconds. So velocity and acceleration. Velocity is basically the first derivative of the displacement function, whereas acceleration is the second derivative. So basically, if I get my first derivative of this function and then plug in my 2 seconds there, I'll be able to get that my velocity shall be negative 3 meters per second. Now that is your answer. Velocity is negative 3 meters per second. Do not be surprised that it's negative, because velocity is a vector quantity. It has direction and magnitude. So the magnitude is 3 meters per second and the direction is in the opposite direction of our positive convention. So if we had assumed that this direction is positive, then it's going in the opposite direction. I've written here, but and there shall be some works that shall be brought here, but don't worry, I'll be able to explain that. What about acceleration? Differentiate it again. You'll find that you'll have 2t minus 6. I believe you can follow it up from even here. 2t minus 6. And if I substitute for 2 there, I'll find that my acceleration is negative 2 meters per second. So that is acceleration. What does it mean? This person was retarding. That's what it simply means. He was slowing down at that particular rate. Now, what about question 2? Time when the particle is momentarily at rest. It means that the velocity is at 0. It's momentarily at rest. It's not moving. So if that is the case, then you bring out the velocity function, then equate it to 0. And then solve your quadratic equation, whereby you know that t shall be 1 second and the second t shall be 5 seconds. So that is the time when the particle is momentarily at rest. Number 3, time when the acceleration is 20 meters per square second. I basically have my acceleration function, plug in whatever I have and what the unknown that I'm looking for. You will figure out that t is the unknown and t will be 13 seconds from what we shall have found out. Now, what about maximum displacement attained by the particle? The maximum displacement attained by the particle is the particular distance that it has covered, the highest distance it has covered, and that highest distance covered is because of the is covered when the velocity is maximum. And when the velocity is maximum, acceleration is usually 0. The reason being, it's not accelerating anymore. So that's why we say the acceleration is 0. And if substitute into my acceleration function, you'll find t to be 3 seconds. Now, these 3 seconds shall be what we shall now come and substitute it into this formula. Now, I'm sorry I did not do that here. So, would you be so kind to do it with me? I shall tell you the answer. So basically, I'll substitute my t 3 seconds into this particular function. Reason being, it is now the displacement function. So s will be equal to 3 cubed, which is 27, divided by 3, which basically gives you 9, multiplied by 3 squared is 9, multiplied by 3 is 27, plus 5 multiplied, that is 15. So I'm at 5t. 5t, if you substitute 3, that's 15, plus 10 gives you 7 meters. So the maximum displacement covered is 7 meters. So I can write it here for you, 7 meters. That's the maximum displacement covered or attained by that particle. Now, what about the displacement covered by the particle during the 5th second? Now, that particular displacement shall be the difference between the displacement at the 5th second and the displacement at the 4th second. So basically, if I have my equation there, I basically pick out this and substitute by 5 and by 4. I'll basically find that displacement shall be equal to negative 1 over 2 over 3 meters. And displacement is also a vector quantity. It also has that particular negative aspect. Example number 2. A solid cylindrical piece of tool has a volume of 7 pi cubic centimeters. Find its radius if the total surface area is to be maximum and hence its maximum surface area. Very good question. Would you please be so kind, if you don't mind, pause the video and then tackle that? I suppose you have something ready. In this particular question, we basically have been told some various aspects. One, it's a cylindrical piece. It means we know how it has a formula of calculating its volume. We know that the volume, the derivative can be used to find maximum and minimum areas, volumes, etc. So basically, my minimum or maximum volume will be equal to the dv over dimension. Dimension shall be either the radius or the height, whatever it is, which shall be equal to 0. So at maximum volume or minimum volume, the derivative of that shall be 0. That's what my equation will mean. So basically, the formula we know is volume is equal to pi r squared h, whereby the volume is 7 pi is equals to pi r squared h. And if substitute to be able to get h, you'll find that h is 7 over r squared. Now, surface area is equals to the top surface, that because it's solid cylindrical piece of tool, it means it is closed on both sides. So it means there is the top surface area, which is pi r squared, the first one, then the bottom surface area, which is pi r squared again, then the curved surface area, which is pi r h, 2 pi r. 2 pi r simply will give you the circumference, h will give it, h is the height, which gives you the curved surface area. If you sum everything there, it shall give you 2 pi r squared plus 2 pi r h. That is the total surface area. Substituting now for h so that we have one kind of, sorry for that, so that we have one type of unknown, or basically a figure that we can use to be able to get our values. We can either use h or we can use r, depending with what we shall have substituted. For me, I've substituted for h. So basically, if I substitute for h, I'll be able to have this, whereby you will know that 2 pi r squared plus 14 pi over r, whereby I believe you saw how r disappeared. R cancelled with one r here, it remained with this. Now if I simplify that, my area, which is still the surface area, I'm writing area because I want to differentiate. I want to differentiate with respect to a, not ds. I'll have a very long statement. So I just want dA. So my dA will be equal to this. So 2 pi r squared plus 14 pi r negative 1. So maximum area occur when the derivative of area with respect to r will be 0. I believe you are following. If I bring that here, if I differentiate now my area with respect to whatever I have, what I'm looking for is basically the radius. I believe you can see what will be happening. So if I bring out that aspect, I'll find that 4 pi r will be equal to 14 pi r raised to power negative 2. Simplify out everything, you'll find that 4 is equals to 14 r raised to power negative 3. Simplifying it further, I'll have that whereby r cubed will be equal to 14 over 4. So if I cube root both sides, I'll be able to find that my radius will be 1.518 centimeters. Plugging this into the general equation of surface area, I'll find that my surface area, this was not it is not supposed to be cubed, it's supposed to be squared. And I was surprised about these units. So this will give you 43.45233.835 square centimeters, not cubed. Sorry for that. So otherwise, this is where we shall pause our differentiation at, and then it shall now be upon you to be able to look for more questions to tackle, so that you may be well acquainted with the particular topic. Otherwise, success in your preparations. May God bless you abundantly.